Last time we started on section 5.2, our last section of new material, talking about multiplication and division of integers. We talked a bit last time about the models for multiplication. I showed you a chip model, a charged field model, and then the number line model. And we talked about one definition. It's not the only one, but this is one definition of integer multiplication in dealing with signs on our values. So what we're going to do next is we're going to move into properties of multiplication for integers specifically. And again, just like when we did them for whole numbers, almost all these are going to look just like they looked before. So do you remember what closure says? Every time I say this, you guys get really quiet. What does closure tell you? That's commutative. I'll do the next one there since you've got that one down. That's commutative. A times B is equal to B times A. So we'll skip the first one for a second. So this is talking about order. Commutative talks about the order not mattering, right? 5 times negative 2 is the same as negative 2 times 5. We already had that property before. Okay, let's go back up to closure. Remember what closure does. Closure is the one that you always take for granted. There's a lot of these you take for granted. But all closure does is say that if I multiply two integers, I get an integer. Okay? We had it for addition. If I add two integers, I get an integer. We had it for whole numbers. If I multiply two whole numbers, or if I add two whole numbers, I get a whole number. So it's saying that I don't get anything else to show up. Square roots do not just all of a sudden just show up out of nowhere. Right? I don't all of a sudden get a fraction or a decimal. That can't happen when I multiply integers. So this is saying that if I take A times B, this is a unique integer. Just get another integer. Okay, commutative we already did. So how about associative? I need 3 letters for associative. What does associative look like? B
plus C.
Not plus C, times C. The plus one we'll get when we get to distributive. Okay, so what would this equal with the associative property? A, B, and then times C. Okay, so associative keeps the letter order the same. Okay, the number order, whatever, the same. The numbers don't change their location. It goes A, B, C, A, B, C. What changed location were what the parentheses was grouping together. On the left-hand side, it's grouping together the B and the C. And on the right-hand side, it's grouping together the A and the B. This is what allows us to do some of those properties you did before about compatible numbers, right? Where we said, I got this whole list of numbers that I'm going to be adding together, and I can add them in any order. So I'm going to add the number at the beginning and the number at the front at the end together, you know, because they're nicer to add together. They equal 10 or 100 or something like that. And we did it for multiplication. Oh man, it's so much easier if I multiply by 10 than if I multiply by 2 and 8 and 6 before I get to the 10. There's a way to sort of rearrange the multiplication so that I can actually make the multiplication easier in the end. And that's what associative property lets me do. It lets me rearrange the grouping of numbers together. I can change the order as well, and that's what I did with the commutative property. All right, we have 3 more. The identity property. So, a few of you are still working on test corrections that involve identity questions. What is the identity element of multiplication?
Is that 0?
It's 1. 0 for addition, 1 for multiplication. All that means is that 0 is the unique number for addition, and 1 is the unique number for multiplication, where when I operate with it, I don't change anything. So the identity property says that 1 is the unique, it's the only one, integer such that 1 times A equals A times 1, which equals A. That's what it takes to be an identity. You operate with it, in this case with multiplication, and it leaves it unchanged. And it feels funny to sort of describe it this way because, like, well, what's the point then? But the reality is that when you get to multiplication and addition with, especially addition and subtraction actually, with fractions, you really like this property because it leaves it unchanged as long as you multiply the numerator and the denominator by something. That's the number 1. So the fact that there is something that you can multiply the numerator and denominator by that equals 1 allows you to use this identity property. It leaves it unchanged, it's just in a different form. So that's where we actually see it coming into places later on with fractions. Distributive property, Colton had already started to tell me because it's the one that has the addition and the subtraction combined with the multiplication. So A times B plus C, and you could say B plus or minus, it doesn't matter, is equal to AB plus or minus AC. And while it works for the multiplication factor to be in front, it also works for it to be sort of in back. If I did the B plus or minus C first and then to times A, the result is the same thing. It would be AB plus or minus AC. And if you want to write BA and CA, that's fine. It doesn't change anything because it's commutative, right? Multiplication is commutative. And then the last property is the zero multiplication property of integers. Same zero multiplication property that we had when we did it for whole numbers. What is true about 0?
A times 0 equals 0 times
Yeah.
A, which equals 0.
You get zeros. It zeroes everything out. And it's the unique integer that does that. So 0 is the unique integer such that 0 times A equals A times 0, which equals 0. Do you feel like we've been doing the same properties over and over and over again? It should feel like it because they never change. It's the same properties. You're just expanding what numbers they apply to, right? So take a look. You've got 4 examples, and I'd like for you to write down which property you think is present in the examples given. And then check in with a neighbor and see if you have the same thing. Okay, what property did you decide the first one was? It's closure. If you remember some of those symbols, that E-looking symbol means is an element of. It means it's one of those next items. And I, in your book anyway, stands for integers. It's not actually what I usually stands for, but that's okay. Your book does it that way. So this is closure. What about the second one? That's the zero multiplication property. How about the third one? Distributive, right? Distributive property is the only one that combines multiplication, distributive, with addition or subtraction. And then how about that last one? That's commutative. Good job, guys. Lovely. All right, a few more facts to finish up for today about integers, some multiplication facts. For every integer, if you multiply a negative 1 times a, it will be the opposite or the additive inverse of a. For all integers, if you have negative a times b, this is equal to negative of a times b. And when you multiply two negatives, negative a and negative b, you get ab. And then I guess I actually had theorem 5.8, which was a separate one. I kind of combined it earlier, so sorry about that. I forgot. With my distributive properties. This is specifically distributive property for subtraction. That'll work. And then we're going to touch on some division properties. All right, integer division. The definition looks almost identical to whole number division. For all integers a and b, a divided by b is the unique integer c if it exists such that a is equal to b times c. So obviously not all integers divide and give us integers. That's why this says if it exists. Okay, it doesn't have to give us an integer when it does it. But if in fact I can divide the numbers 6 and negative 2, the reason that this works is because, I should say, the reason that 6 divided by negative 2 is what? Negative 3, right? Is because 6 is equal to negative 2 times negative 3. And that's what the definition is saying. The reason it equals an integer is because it can be changed into a statement about multiplication that is equally true. Back in section 4.1, we talked about things dividing, and in particular, we looked at whole number division, but I made the mention that it was actually true for integers as well, and so this is what this is talking about for divisibility. If a divided by b is a unique integer, then a is divisible by b, or equivalently, b divides a. So again, I'll just use my 6 and my 2 from the previous screen. So 6 divided by negative 2 is a unique integer, correct? It's negative 3. Then we would say that a, 6, is divisible by negative 2. And we can also, or we could say negative, these are different statements that are all equivalent. Negative 2 divides 6. And notationally, we talked about that being this vertical bar. Negative 2 divides 6 like that. So this is all just rehashing what we already know, but applying it in the context of integers. The next one, just another piece from the past popping back up for us, is inequalities. For all integers a and b, a is less than b, written a less than b, if and only if there is there exists a positive integer k such that a plus k is equal to b. And just for the sake of seeing it we've seen this with whole numbers, let's do it with some negatives. So the reason that negative 2 is less than, say, negative 1 is because I can take negative 2 and I can add something to it to equal negative 1. What would I have to add to negative 2 to get to negative 1? 1. And so that's my k value. And you'll notice k has to be a positive integer for this to make sense. If I could add negative 3 or negative 1, it wouldn't make sense, right? Because adding a negative would actually make it smaller, not bigger. So we can't actually just add any integer. We still have to add a positive integer, k. Just notationally, Theorem 5.9 says, for integers a and b, a is less than b if and only if b minus a is equal to a positive integer. So again, let me use the ones I just did. This is negative 2 is less than negative 1. So if negative 2 is less than negative 1, it means that I should be able to take that negative 1, which is my b, and subtract negative 2 and equal something that's positive. But what happens when I subtract my negative 2? It's a positive. That's right, Brianna. So we'll get positives there. And so what is negative 1 and positive 2? It's 1. And sure enough, that is in fact bigger than 0. Okay? And if you think about it from a number line perspective, you guys know I'm all about visuals because that's how I think. But if you think about it from a number line perspective of where these numbers are, here's 0, here's -2, and here's -1. What you're saying is that if you start here, that the distance it takes to go back over here is going to be a positive distance, right? If I subtract from the right to the left, I'm ending up with a positive number. Clearly, if I went the other direction, that wouldn't happen, right? -2 minus 1, I would not end up with a positive number if I subtracted moving to the right. So, all right, theorem 510. X and Y and N are all integers. And there's a few ones here I'm going to write in with you. So the first one says if X is less than Y, then X plus N is less than Y plus N. We saw this with whole numbers as well. I'm sure I gave some example about me standing up here with somebody standing beside me and saying if we all put on 3-inch heels, our distances and our heights would still be the same, right? The differences would still be the same. So all you're doing is you're saying these two numbers are right here on the number line. If I add something to it, they're still the same distance apart on the number line, right? It doesn't change where they are, how far apart they are just by changing where they are. The next one, again, X is less than Y, tells you that if you take negative X and negative Y, what do you suppose happens to your inequality? It reverses. So now this is actually going to be greater than. And if you do a number example, you will recognize this very quickly. So, for instance, 2 is less than 7. No problem, right? But think about -2 and -7 on a -7 on a number line. Which one's bigger? The -2 is bigger, right? So the inequality symbol changes when the numbers are multiplied by a -1 or divided by a -1. It works both directions. However, on part B, or C rather here, the third piece says that if you actually have a positive number, right? So X is less than Y and N is positive and you multiply by it, the direction of the inequality stays the same. I need to move that. Right, so again, let me use my 2 is less than 7 one. If I multiplied each of these by a positive number, say 3, I'm going to get 6 and I'm going to get 21. Does my direction of my inequality stay the same? Absolutely. But it's because I multiplied by a positive. So multiplying by a positive number does not change the direction of the inequality. I already said if I multiplied by a -1 or I switched the signs that it changed it. But it's actually not just so specific to -1, but if n were less than 0, any number negative, it will change the direction of the equality. So let me use the same thing up here, but we'll multiply by -3. So if I multiply by -3 and I get -6 and I get -21, which one's bigger? -6 is bigger. All right, and bigger again means closer to 0, or sorry, closer to the right-hand side, let me say it that way, on the number line. All right, our last examples for the semester. Example number 5. Yay! We'll do them one at a time. There's lots of ways to do these. I am not teaching you algebra at the moment. That is not the goal. So there's more than one way. You could guess and check this, and we would be okay with it. Okay? I'm going to show you how to do it in a couple of ways besides guess and check, because I know you know how to do guess and check. But I'm going to show you a couple of algebra techniques that are possible. One technique that's possible in part is to distribute. Most of you probably were led in that direction when you looked at it. Distribution is a very popular way of doing this problem. So let me show you what it looks like if you choose that option. So if you choose to distribute through, you would multiply your -5 through the parentheses. So I'd get -5x plus 15 equals -5. And then you always move your addition and subtraction first. So we can subtract 15. So I still have -5x on the left. What is -5 and -15? -20. And then I could divide by -5. So what is -20 divided by -5? +4. Okay, so distribution is one option. we already said trial and error or guess and check. That's another option. That's fine. Let me show you one more option that you may not necessarily have thought of quite as quickly, but it works really nicely. It's super friendly that the number that's in front of the parentheses here divides the 5 that's on the other side. That doesn't always happen. I recognize that. But because it divides it, I could actually divide both sides by -5, and these would cancel right here, leaving me with simply x minus 3. And I would have 1 on the right-hand side, and then I can add 4. In terms of efficiency, I'm sorry, add 3 to get 4 is what I meant to say. Ahead of myself. In terms of efficiency, that's super efficient. Way fewer steps. I mean, a lot quicker to get to my answer. But if you don't see it, then it doesn't matter. Don't do it. I mean, that's fine. It's just another option. Okay. And again, not the only options, but there are 2 options that would work. Either way, you're going to get the same answer 4. Checking to make sure that it works is a good idea. You should always be able to do that in the problems that you're given. So if I put in put in 4 minus 3 in parentheses is 1, and 1 times the -5 in front of it would be the -5 that's on the other side. So they do, in fact, match and work out. All right, these 2. Okay, so there's some algebra at play here that we can discuss, and I'll show you how to do that. But there's also a very straightforward way to deal with this that has to do with a question Michaela asked earlier from the homework from last time. What can you tell me about these 2 quantities that are in the parentheses? They're the same thing but flipped, which means they're what compared to one another? They're additive inverses. Do you guys remember this talk, right? We talked about additive inverses. What did I say? Because it was actually Catalina's question, but then you and I had a discussion about it. What did we say has to be true in order for values to be additive inverses by definition? They have to add together to equal 0. Do you guys remember that? Okay, so, and these do, right? If I were to add 1 minus x and x minus 1, I'd get 0. These are additive inverses. So the cool thing about additive inverses is they always create numbers that are the same number in opposite signs. So I'll get 5 and -5, 7 and -7, 12 and -12, 15 and -15. They're always the same, okay? So what I want you to recognize first is what's in the parentheses are the same thing, but the signs don't match, right? So what's going to happen when you square both of them? Then you actually get the signs to match. It's like taking absolute values, right? That same one that you had asked about, Aspen, right? When I square things, when I take absolute values of things, the signs no longer matter because the signs all become positive. So in a very real sense, these are additive inverses, so they give us the same quantity. And because I'm squaring, I get the same signs on both sides, so the answers both work. And the reality is that it works all the time. So actually, x is any integer. Now, I'll show you a concrete way of working it out if you're not connecting with what I'm saying, and that's totally fine if you don't. I just want you to recognize, at least me having said it once, that these are actually the same quantity, but different signs squared. So check it out. What if you had 5 minus 1 and 1 minus 5? What numbers would you be getting? 4 and -4. And what happens when you square 4 and -4? You get 16. We'll try one more just for fun. Instead of 5, let's say you had, you could even use a negative. Let's say you had -2. So what is -2 minus 1? That's -3. What is 1 minus -2?
3.
Yeah, those change. This would be 3. And what happens when you square both of them? You get 9, right? The signs no longer matter. Okay, so let's say that you were looking at that and you weren't connecting those things to begin with. You have lots more going on in your mind than worrying about additive inverses of binomials. So you just start to solve it. What are options for solving it? Well, because both sides are squared, you could square root both sides. Okay? Here's the catch, though. When you take a square root of something, you have to do a plus or minus. So you're going to get 1 minus x. But you're also going to get, this says x minus 1. You're going to get negative x minus 1. I'm running out of space. Okay, so this is the positive part of the square root, and the other one after the or is the negative part of the square root, right? When you square root 70, that's not the number. How about we go with 49? Square root 49, you get plus or minus 7. If you square root 25, you get plus or minus 5. Okay? So on this one, we have x minus 1 equals 1 minus x. And if I add an x, right, I have 2x minus 1 equals 1. And I add a 1, then here I get 2x is equal to 2, and x would then be 1. So in one direction, I get x equal 1. That's fine. X equal 1 is a perfectly fine solution. But over here, this is x minus 1, and then negative x. Did I write them backwards? I'm sorry, I did. Over here, it should say 1 minus x again. They should have stayed the same. My bad. So I have negative 1 plus x. But x minus 1 and negative 1 minus x is x minus 1. These are the same, right? They're exactly the same. And when they're equal to exactly the same, it means any value works. All integers. And you might feel like that makes one sort of like a better answer, but it doesn't. It just means it was already included in the other set to begin with. So again, just another option on how to think about that problem.